Instruction tuning turns a pre-trained language model into one that can respond to human requests in a useful, controlled way. That matters because chatbots and assistants depend on following the prompt, not just predicting text. The focus now is the full workflow, how instruction data is prepared, grouped for training, used to update a pre-trained model, and then checked for quality afterward. The core process starts with examples that pair a user instruction with the response we want the model to produce. Training on those pairs teaches the model the pattern of answering requests directly and consistently. The dataset has to be clean and structured because the model can only learn from the examples it sees. Each sample needs the instruction and the target answer in a format that the training loop can read reliably. Once the examples are ready, they're grouped into batches so training can run efficiently. Batching also helps the model see many instruction styles during each update, which makes learning more stable. The starting point is a model that already knows language patterns from pre-training. Fine-tuning adjusts that model toward instruction-following behavior without relearning language from scratch. After training, the model's answers need to be collected so they can be compared against the desired behavior. That makes it possible to inspect whether the model stays on task and answers in the right style. Evaluation checks whether the tuned model actually follows instructions better than before. The goal is not just fluent text, but responses that are relevant, accurate, and aligned with the prompt. The earlier steps built the model itself and adapted it for a narrow classification job. Now the target changes. Instead of predicting a label, the model must produce a helpful response to a human request, which is the behavior needed for chat and assistant systems. The important split in the figure is between task-specific classification and instruction following. The first path teaches the model to map inputs to labels, while the second path teaches it to generate a response that matches the user's intent. The focus lands on the last step of the development pipeline, taking a pre-trained model and refining it with instruction data. That step is what moves a language model from general text prediction toward conversational use. The classification path uses labeled categories, while instruction tuning uses examples of prompts and answers. That difference matters because the second setup teaches not only what to predict, but how to respond like a useful assistant. Instruction fine-tuning turns a pre-trained language model into a system that can follow direct requests more reliably. The important shift is from simple text completion to producing a response that matches an instruction. A pre-trained model is good at continuing patterns in text, yet that does not automatically make it good at obeying tasks like grammar correction or voice conversion. Instruction fine-tuning closes that gap by training the model on examples of prompts paired with the responses we want. The quality of the dataset determines how well the model learns the prompt response pattern. A clean, well-structured dataset gives the model clear examples of what to do when it sees a new instruction, and the process begins with preparing that data carefully. Focus on the pairings. Each instruction is matched with the response it should produce. That pairing is the training signal, because the model learns not just language, but the mapping from a request to an appropriate answer. The examples make the task concrete. The input is a human instruction, and the target is the response the model should generate. That idea will carry through the whole fine-tuning process. The process has a clear structure. First, prepare the data, then set up and fine-tune the model, and finally evaluate how well it follows instructions. Each stage depends on the one before it, so the data work comes first. The first practical step is getting the dataset into the right shape for training. Once the examples are downloaded and formatted consistently, the model can start learning from them in a reliable way. Supervised instruction fine-tuning starts with a dataset that pairs a task description with the right answer. The goal here is to turn raw examples into a format the model can train on reliably. The dataset is small enough to inspect directly, which makes it ideal for learning the pre-processing steps. Each record links an instruction to a target response, and that structure is what the model will imitate during training. JSON is a good fit because it keeps the data readable for people and easy to load in Python. Since it mirrors dictionaries, each example can carry fields like instruction, input, and output without any extra parsing complexity. The next step is practical. load the file once, save it locally if needed, and then read it into memory. That gives us a clean list of examples to work with. The function first checks whether the file already exists, so it avoids downloading the same data again. If the file is missing, it fetches the JSON text from the URL, writes it to disk, and then loads it back into a Python object with json.load. The final print confirms that the dataset was read correctly. That count is the first sanity check. It tells us the file loaded correctly and that the dataset really contains the expected number of examples. A total of 1,100 entries means we have enough examples to fine-tune on, while still being small enough to inspect and split carefully. This number becomes the basis for the training, validation, and test partitions. Printing one entry reveals the exact structure we need to format later. The important part is that every example stores the task description and the target answer in named fields. Index 50 gives one representative example from a list. Printing it makes the field names explicit, which is useful before we write any formatting code. What matters is the shape of the record, not the specific content. Once the field names are clear, we can build a formatter that turns every dictionary into the same prompt template. This example shows the three core fields: an instruction, an optional input, and the desired output. The model will learn to map the first two fields to the third one. The structure is simple, but that simplicity is exactly what makes the formatting step manageable. The dataset already contains the supervision signal. Our job is to package it in a prompt style the model can read consistently. A second example is useful because not every record uses the same amount of input text. Looking at another index shows how the formatter has to handle both filled and empty input fields. Some tasks only need an instruction and a response. In those cases, the formatting code should omit the input section instead of leaving behind an empty label. This record makes the edge case clear. The input string is empty, but the instruction still fully defines the task. A good prompt template has to adapt to that case cleanly. Fine-tuning works by showing the model the full prompt and the desired completion. Different models use different prompt styles, so the same dataset can be wrapped in more than one template. The figure compares two common ways to wrap the same training example. One format uses labeled sections for instruction, input, and response, while the other uses role tokens that separate user text from assistant text. The left format is more verbose and structured, while the right format is closer to chat history. Both teach the same task, but the surrounding tokens differ, and those tokens matter because the model learns from the exact text pattern. Alpaca is a useful choice here because it became a widely adopted early pattern for instruction tuning. Using one consistent format keeps the rest of the training pipeline easier to build and debug. Changing the prompt wrapper is a good way to test how sensitive the model is to formatting. The underlying examples stay the same, but the training signal can still shift when the template changes. The best way to judge a prompt style is to fine-tune once, then compare how the model responds under a different template. That comparison shows whether the format itself affects learning and generation quality. The format handles the repetitive part of the job. It takes one dictionary at a time and turns its fields into the exact text pattern the model should see during training. The goal now is to build the template once and reuse it for every record. That keeps the dataset consistent and avoids handwriting prompts for individual examples. The first string gives every example the same framing sentence, then inserts the instruction itself. The conditional line is the key idea. If the input field exists, it adds an input section, and if not, it leaves that part out entirely. Testing on a real entry confirms that the template matches the dataset structure. That gives us confidence before we append a response text and train on the result. The first line builds the prompt from the example, and the second line appends the target response in the same structured style. Printing the full string shows exactly what one supervised training sample looks like. At this point, the complete prompt is visible as one training record. The structure makes it clear where the instruction ends and where the expected answer begins. The prompt now reads like a full supervised example: instruction, optional input, and target response. This is the exact text pattern the model will learn to reproduce in the response portion. When the input field is empty, the formatter should not insert a blank label. That keeps the prompt clean and ensures the same template works for both single-field and two-field examples. This test uses an example with no input text, so the conditional branch in the format matters. The prompt should jump straight from the instruction to the response marker without any extra placeholder section. That behavior confirms the formatter is handling the optional field correctly. A model training prompt should reflect the actual data, not force every record into the same rigid shape. The absence of the input section makes the example shorter, but the supervision signal is still complete. The model only needs the instruction and the desired answer to learn this kind of task. Before batching begins, the data needs to be divided into separate subsets. Training data is used for learning, validation data for tuning decisions, and test data for a final check on generalization. A clean split protects the evaluation procedure. Once the sizes are fixed, each subset can serve its own role without overlap or leakage. The percentages are computed from the full dataset length. Then the list is sliced into 3 contiguous chunks. Using the remainder for validation avoids rounding problems, and the print statements verify that the split adds up correctly. These proportions give the model most of the data for learning while keeping enough held out for evaluation. The small validation set is still useful because it guides model choices during development. The counts let us verify that the arithmetic matches the intended proportions. If the totals look right, the split is ready for the loader stage. Those numbers reflect the chosen October 5th, 85 split of 1,100 examples. The important point is that each subset has a clear role, and none of them overlap. The data is now downloaded, formatted, and partitioned, so the last missing piece is batching it for training. After this, the input pipeline can feed the fine-tuning loop with consistent examples. Training batches are the bridge between formatted examples and model updates. The main job here is to prepare each instruction response pair so the model can consume them efficiently during fine-tuning. The implementation starts with batch construction because the model cannot train on raw records directly. Each example has to be formatted in a consistent way before it can be grouped with others and passed through the network. The diagram separates the process into stages so the data flow stays clear. Focus on where formatting ends and batching begins, because that boundary determines how the dataset will be turned into model-ready tensors. Step 2 is where the pre-processed examples start becoming actual training batches. That matters because the model learns from grouped sequences, not from isolated text strings. PyTorch normally handles this for us with a default collate function. The collate function takes a list of individual samples and merges them into one batch tensor that the model can process efficiently. Instruction tuning is more specific than ordinary classification, so the default batching logic is not enough. A custom collate function lets us control formatting, padding, and target construction in a way that fits the dataset exactly. The dataset class does the first part of the work up front. It applies the prompt template and turns every completed example into token IDs. Doing that in the constructor keeps later batching simpler and faster because the heavy text processing is already done. The 5 substeps make the batching logic much easier to reason about. Keep track of the sequence from formatting to tokenization to padding to targets and finally to masking because that is the full path from raw example to training loss. The key detail is that batching is not just stacking lists together. It also includes deciding which tokens should count in the loss and which tokens should be ignored during training. The first 2 steps happen before batching ever starts. The prompt template is applied, and the text is tokenized into IDs. Those IDs are what the model actually sees, so this is where the dataset becomes machine-readable. That order matters. The model should learn from the exact instruction response format we want at training time, and tokenization turns that formatted text into the numeric sequence the network can use. The dataset class stores pre-computed token sequences instead of raw strings. That lets the later collate function focus on padding and alignment, rather than repeatedly rebuilding the same text representations. The constructor loops through every record, formats the prompt, appends the expected response marker, and then tokenizes the full text right away. The important idea is that __get_item__ later returns a ready-made list of token IDs, so the dataset is already pre-processed before batching begins. Pre-tokenizing moves the text-to-token conversion out of the training loop. That saves repeated work and makes each batch operation lighter. Padding is necessary because sequences in a batch must line up to the same length. Reusing the end-of-text token keeps the implementation simple, and we can still distinguish real targets from padding later. It is cleaner to work with token IDs directly once the text has been encoded. Calling encode on the special token tells us which integer to append whenever we need padding. The tokenizer is asked to encode the special end-of-text symbol, and the allowed underscore special argument makes that possible. The printed number is the exact token ID we will reuse as padding in the batch builder. That numeric ID is the value the batching code will append when it needs a padding token. Using the ID directly is faster and avoids working with text strings inside the collation step. The next improvement is to pad only within a batch, not across the entire dataset. That keeps padding overhead low, because each batch stretches only as far as its longest example. The two batches may end up with different final lengths, but every example inside one batch lines up perfectly. Track how the padding token fills the short sequences while leaving the longer ones unchanged. That local padding strategy is efficient and practical. It gives the model uniform shapes for computation without forcing every batch to match the maximum length in the whole dataset. The batching logic now needs to do the padding work that data loader will rely on. Once that function is written, it can turn a list of variable length examples into a single tensor batch. The function finds the longest example, adds one padding token so the shifted target logic will work later, and then pads every item to the same length. After trimming the extra trailing token, it stacks the results into one tensor and moves that tensor to the target device. Each numbered step serves one clear purpose. The first finds the working length for the batch, the second builds padded examples, the third prepares the input shape, and the fourth turns the list into a tensor the model can use. Running the function directly is a good way to verify the padding logic before plugging it into a data loader. A small test batch makes it easy to see whether shorter sequences are being extended correctly. These three lists give us different sequence lengths, which is exactly what the collate function has to handle. The print call checks whether the shorter lists get padded up to the length of the longest one. The output should make the padding pattern obvious. The first row stays untouched, while the shorter rows pick up padding IDs at the end until all rows have the same length. The first sequence already has the maximum length, so it stays unchanged. The other two sequences are extended with 50,256 until every row has 5 token IDs. That confirms the batching rule is working. Every example in the batch now has the same width, which is required for efficient tensor operations. Inputs alone are not enough for training, because the model also needs the shifted targets it should learn to predict. The collate function, therefore, has to return both the input IDs and the target IDs. Focus on the target side of the diagram. The goal is not just to pad inputs, but to build the matching target sequence that will drive the loss calculation during training. Step 2.4 adds the learning signal. Once the target IDs are built, the model can compare its predictions against the correct next tokens and update its weights. The target sequence is just the input sequence shifted forward by 1 token. That alignment teaches the model to predict the next token at each position, which is the core language model training objective. Watch the alignment between the input row and the target row. The target sequence starts one step later, so every prediction is compared against the token that really comes next. That shift is what turns token sequences into a next token prediction problem. The model sees one token and is trained to predict the one that follows it. The updated collate function now needs to produce both tensors at once. That keeps the input-target pairing aligned inside each batch, which is important for loss computation. The same padded list now produces 2 views. The input slice drops the last token, and the target slice drops the first token. That 1 token shift is exactly what we need for next token prediction, and stacking both lists gives us matching batches. The inputs and targets are nearly identical, but they are offset by 1 position. That offset is what lets the model learn to predict the next token instead of copying the current one. Applied to the sample batch, the function produces two aligned tensors. One is fed into the model, and the other becomes the supervision signal for training. The first tensor is the input batch, and the second tensor is the shifted target batch. Notice how the second row and third row still contain padding positions, because those positions will be handled separately in the next step. The pairing is now explicit. One tensor provides the context, and the other provides the expected next tokens. That separation is what makes supervised language model training possible. Padding still appears in the target batch, but those positions should not influence the loss. Replacing them with -100 tells PyTorch to ignore those entries during cross-entropy calculation. Track the target side, where padding tokens are being replaced. The important part is that real target tokens remain, while the extra padded positions are turned into ignored labels. This is the masking step. It keeps the useful target tokens intact and removes the padding tokens from the loss calculation. One end of text token is still useful because the model should learn when to stop generating. The extra padding copies are ignored, but that first end of text token remains as a real training signal. Pay attention to the first end-of-text token versus the later padding copies. Only the first one is kept as a genuine target. The rest are replaced so they do not affect training. The target sequence still needs a stopping signal. Masking only the padding copies preserves that signal while preventing the loss from being diluted by repeated padding tokens. The final version of the collate function adds two practical features. It masks padding tokens in the targets and can optionally cut sequences to a maximum length. That makes the code safer for longer datasets that exceed the model's context window. This version brings the whole batching pipeline together. It pads, shifts, masks, and optionally truncates, so the resulting batches are ready for training. The function pads each sequence, creates the shifted targets, and then replaces every padding target after the first with the ignore index. If a maximum length is supplied, both tensors are trimmed to that limit before being stacked and moved to the device. The numbered comments show the whole pipeline in order. First, the examples are padded, then inputs and targets are separated, then the padding labels are removed from the loss, and finally the batch can be clipped if needed. A quick test on the same 3 sequences verifies that the new masking logic still preserves alignment. The output should now show real targets where learning should happen and ignored positions where padding begins. The same sample batch is passed through the final collate function. Printing both tensors makes it easy to compare the shifted inputs with the masked targets. The first tensor remains the model input, and the second tensor is now the training target with ignored padding positions. That is the format the loss function expects. The input batch is unchanged, but the target batch now has -100 wherever padding should be ignored. The first end-of-text token is still present, so the model can learn both how to continue and how to stop. That masking changes training, not the input data itself. The model still sees the padded batch, but the loss function only measures the meaningful target positions. A small numeric example makes the masking rule easier to see. By comparing a short target sequence with a longer one, we can check exactly which entries contribute to the loss. These logits represent predictions for 2 positions, and the target vector gives the correct token index for each one. Cross-entropy compares the predicted distribution to those labels and returns a single loss value. Each row of logits corresponds to one position in the sequence. The loss function evaluates both rows against their matching target labels. The value 1.1269 is the baseline loss for that 2-step prediction problem. It gives us a reference point before we add another target position. That output is the numeric cross entropy for the 2-token case. It becomes the comparison point for the longer target sequence. If we include another prediction position, the loss changes because the model is now being judged on one more target. More supervised positions usually mean a different aggregate value. The third row adds one more prediction and one more target label. Cross-entropy now includes that extra position when it computes the average loss. That extra row is a new supervised prediction. It contributes to the loss exactly like the earlier positions do. The loss drops to 0.7936 because the prediction set has changed. Now the model is being scored on 3 positions instead of 2. Masking becomes visible when one of those target entries is set to -100. If the loss function ignores that entry, the result should match the shorter two-token case. The final target entry is replaced with -100, so cross-entropy skips it entirely. The comparison line checks whether the masked three-token loss matches the original two-token loss. The printed result should match the shorter example exactly. That confirms the ignored entry contributes nothing to the loss. The masked loss is identical to the two-token loss, and the equality check returns true. That tells us the -100 label is being ignored exactly as intended. That behavior comes from PyTorch's default ignore_index setting. Replacing padding targets with -100 removes them from the loss calculation, while keeping one end-of-text token still teaches the model when to stop generating. The special value is not magical by itself. It is special because the loss function is configured to skip it. We use that to hide padding, but we preserve one real end-of-text label so the model learns completion as well as content. Padding is not the only thing you can mask. Some setups also hide the instruction part of the target sequence, so the loss focuses only on the generated answer, which can change how the model learns. Compare the left side and the right side carefully. The left shows the formatted text that gets tokenized, and the right shows the target tokens where the instruction portion may be replaced with -100. The key choice is whether the loss should cover the instruction tokens or only the answer tokens. Masking the instruction side narrows training to the response, while leaving it unmasked asks the model to learn the whole sequence. Research is still mixed on whether instruction masking always helps. In this chapter, the safer choice is to leave the instructions unmasked and treat masking as an experiment you can test later on your own data. The exercise asks you to try the masking variant yourself after training with the unmasked version. That comparison will tell you whether your dataset benefits from training only on the response tokens. The practical test is simple. Train once with instruction masking, then compare the results against the unmasked setup. The performance difference will show whether masking helps on your own task. Data loaders turn the instruction dataset into batches the model can actually train on. The important part is that the dataset, the collate function, and a loader now fit together as one pipeline. The work so far pays off here. The dataset knows how to provide examples, and the collate function knows how to assemble them into batches. Once those pieces are handed to a data loader, shuffling, batching, and preparation for fine-tuning happen automatically. Track the flow from raw instruction data to prepared batches, then into training and evaluation. The figure ties the earlier pre-processing steps to the loader setup, so the whole path to fine-tuning stays organized. The dataset is ready, and the batching logic is in place. What remains is wiring both pieces into the loaders for training, validation, and test data so the model can be evaluated cleanly. The collate function can also place tensors on the right device while it builds a batch. That matters because the data transfer happens outside the main training loop, which keeps the GPU from sitting idle while batches are being prepared. On Apple Silicon, the MPS backend can work, but its numerical results may differ slightly from the values reported here. That is a backend issue, not a problem with the batching logic. Putting the transfer in the collate function makes the loader do the work in the background. The training loop then receives ready-to-use tensors instead of spending time moving each batch by hand. The device choice is determined once at the start, so the rest of the code can reuse it consistently. That keeps the batching code simple and lets the same script run on CPU or GPU without changes. The first line chooses CUDA when it is available and falls back to CPU otherwise. The commented lines show the Apple Silicon option, and the print statement confirms which backend the script picked before any loading begins. That note points to the optional branch for Macs with Apple Silicon chips. Leaving it commented keeps the default behavior simple, but the option is there when the hardware supports it. The printout tells you which execution path is active on the current machine. A CPU-only system will report CPU, while a machine with a working NVIDIA GPU will report CUDA. Partial function application fixes the device and the maximum sequence length ahead of time. That way, the data loader can call a single collate function without needing extra arguments for every batch it builds. The partial call creates a configured version of the collate function. The two fixed arguments matter most. One sends tensors to the chosen device, and the other trims sequences to GPT-2's context limit. With that configured collate function in hand, the loaders can behave like standard PyTorch loaders while still handling the special batching logic needed for instruction data. The setup stays familiar, but the batch preparation is now tailored to this task. The loader setup is the bridge between prepared data and model training. Each split gets its own loader, and each loader uses the same batching rules so training and evaluation stay consistent. The training loader shuffles examples and drops the last partial batch, so every step sees the same batch size. Validation and test loaders keep the order and preserve all samples, which is important when you want evaluation to be stable and reproducible. The worker count can be raised when the operating system allows parallel Python processes. More workers can speed up loading, but the safe default is 0 on systems where parallelism is limited. Printing the shapes is a quick way to verify that the loader is assembling data correctly. The batch size should stay fixed, while the sequence length can vary from batch to batch because of the custom collate function. This loop walks through the training loader and reports the size of each input target pair. The shapes tell you whether batching and padding are working the way the model expects. The printed batches are enough to confirm the pattern without showing every single batch. What matters is that the loader produces a sequence of batch shapes, rather than one fixed length for all examples. Each pair has the same input and target shape, and the first dimension stays at 8 because that is the batch size. The second dimension changes from batch to batch, which shows that sequences are being grouped and padded dynamically instead of forced into one fixed length. That variation is exactly what the custom collate function is meant to handle. With the loaders working this way, the fine-tuning code can focus on the model instead of the bookkeeping around batching. Loading a pre-trained language model gives us the starting point for instruction fine-tuning. The important idea is that most of the training pipeline stays the same, so the earlier code can be reused instead of rebuilt from scratch. The dataset changes for supervised fine-tuning, but the surrounding machinery does not need to change much. That is what makes this stage efficient. Once the input format is ready, The model loading and training logic can follow the same pattern used earlier. The model needs enough capacity to learn instruction following behavior, which is why the larger GPT-2 medium checkpoint is used here. A smaller model can memorize patterns, but it usually struggles to keep the more subtle instruction-response relationships stable during fine-tuning. The process starts with a pre-trained base model, then fine-tuning adapts it to instruction data. The checkpoint is the foundation. Without it, the later training stage would begin from random weights instead of useful language knowledge. The figure ties the sequence together. Prepare the dataset, load the pre-trained model, then train on instruction examples. That ordering matters because the model cannot learn the task format until the data and starting weights are both in place. The loading pattern is familiar, so the main change is just the checkpoint name. The configuration expands to match the larger model, and that gives the fine-tuning step a stronger starting point than the small network used earlier. That size difference matters in practice because a larger checkpoint takes longer to download and more disk space to store. The extra cost is the trade-off for having a model with enough capacity to respond well to instruction data. The code now turns the chosen checkpoint into a working GPT model. The key pieces are the configuration, the downloaded weights, and the final switch to evaluation mode before we test any generation. The configuration sets the shared GPT settings first, then plugs in the architecture details for the selected checkpoint. After that, the weights are downloaded, loaded into the model, and the model is put into evaluation mode so dropout stays off during inference. Those files are the pieces needed to reconstruct the pre-trained model locally. Some hold the weights, while others define the tokenizer and model metadata that make the checkpoint usable. The download log confirms that the full pre-trained package has arrived, including the large weight file and the tokenizer assets. The long weight download is the main cost here, and the smaller files are what let the model decode text correctly. Before changing any weights, it helps to measure the starting point on a real instruction task. That baseline tells us whether the model already follows the prompt or whether fine-tuning still has a lot of work to do. The random seed keeps the generation deterministic, and the first validation example is formatted into the prompt style the model expects. Printing that prompt makes it easier to compare the instruction with the response the model produces. The template frames the task clearly, so the model receives both the instruction and the expected response format. That structure matters because the model needs to learn not just language, but the pattern of responding to a prompt. The task itself is a simple transformation. Change an active sentence into passive voice. That makes a good test case because the correct answer requires following the instruction rather than just repeating the input. The same generation routine can be reused because the model still works one token at a time. What changes now is not the decoding method, but whether the model has learned to produce the right kind of completion for an instruction prompt. The prompt is converted to token IDs, then the generator extends it for up to 35 new tokens within the model's context window. After decoding, the result includes both the original prompt and the continuation, so the full text can be inspected before isolating the answer. Autoregressive models naturally append new text to what they were given, so the output arrives as one continuous string. That is useful for completion tasks, but it means evaluation needs a separate step to separate the model's answer from the prompt. The response begins right after the original input, so slicing by the input length cleanly separates the continuation. Trimming whitespace afterward makes the extracted answer easier to inspect and compare. The slice starts at the first character after the prompt and keeps everything the model generated. The final strip call removes stray spaces and line breaks, which gives a cleaner response for evaluation. That small slicing step changes the full completion into a usable answer string. It is a simple but important evaluation trick whenever the model output contains the prompt and response together. The model falls back to copying the input instead of transforming it, and it even starts repeating the instruction afterward. That behavior shows the pre-trained model understands text continuity, but it has not yet learned to follow the task the way an instruction-tuned model should. The baseline is weak, and that is exactly why the next step matters. Fine-tuning will teach the model to shift from plain text continuation toward task-following behavior that answers the prompt directly. Instruction fine-tuning takes a pre-trained language model and teaches it to follow prompts more reliably. The goal here is to turn a general text model into one that can answer task-style requests in the format we prepared earlier. The main setup is already done. A pre-trained model is loaded, and the instruction dataset has been processed into the right form. That means the training loop can focus on learning from the instruction examples instead of rebuilding all the data machinery. The figure organizes the workflow into stages, and the important idea is that the final step uses the pre-trained model together with the instruction dataset. That is where the generic model starts adapting toward instruction following behavior. This last stage is the actual adaptation step. The model has already been loaded, and now the parameters are adjusted so its outputs match the instruction targets more closely. Two utilities from the earlier training chapter do the heavy lifting here. One measures loss over a loader, and the other runs the training loop, so the fine-tuning code stays compact and reusable. Before updating any weights, it helps to know where the model stands. That starting loss gives a baseline, so later changes in training and validation loss have something concrete to compare against. The model is moved onto the selected device, and the random seed keeps the result reproducible. Then the loss is computed on a few batches from the training and validation loaders without gradients, which gives a quick snapshot of how well the loaded model fits the instruction data before any fine-tuning. Those numbers are not the final goal. They're the starting point. Fine-tuning matters only if it pushes both losses downward while keeping the validation result under control. These values show the model is starting from a fairly high error level. The task now is to reduce both numbers, which means the model is learning the instruction format rather than guessing randomly. Model size and hardware capacity matter a lot at this stage. If memory or runtime becomes a problem, the practical response is to reduce the model size or move the work to a GPU. A 355 million parameter model puts more pressure on memory and compute than the 124 million parameter version. When resources are tight, dropping to the smaller model is the simplest fix, and a GPU can speed training without changing the code logic. The important point is that the training code stays the same across devices. What changes is the execution time, and that difference can be large enough to decide whether fine-tuning is practical on a given machine. The table compares the same training job across CPUs and GPUs, and the gap is striking. Larger models and slower devices stretch the runtime, while an A100 makes the same work finish in a fraction of the time. Once the data loaders are ready, training becomes a standard optimization problem. The code sets the learning rate, the epoch count, and the prompt used to check the model's generated response during training. The training script ties the whole process together. It initializes optimization, runs for a small number of epochs, and periodically checks whether the model is improving on held-out instruction examples. The optimizer uses AtomW with a small learning rate and weight decay, which helps make fine-tuning stable. Training runs for 2 epochs, and the evaluation prompt comes from the first validation example, so the model's response can be tracked during learning. Timing the run at the end gives a practical sense of cost as well as accuracy. The output combines 2 signals, loss values and example completions. When both trend in the right direction, it means the model is not only optimizing numerically, but also getting better at producing the kind of answer the instruction asks for. The first epoch makes the biggest jump, which is common when a pre-trained model adapts quickly to a new data format. By the second epoch, the losses are lower and changing more slowly, and the sample generations show the model moving from a rough paraphrase toward the correct passive construction. The final prompt is also a useful sanity check. The model is beginning to answer instruction-style questions in the expected format. The downward trend means learning is happening, but validation loss should not be forced lower at any cost. Once training has already captured the main instruction patterns, extra epochs can start to memorize details instead of improving general response quality. The generated example is the clearest sign of progress because it checks actual task behavior, not just a loss number. Getting from active to passive voice shows the model has learned to transform the sentence structure the instruction asked for. A plot makes the learning trend easier to read than raw numbers alone. It shows whether the model is converging smoothly and whether the validation curve is tracking the training curve or beginning to drift away. The same plotting utility from earlier turns the recorded losses into a graph against tokens seen and epic progress. That lets the training trajectory and the validation trajectory be compared on the same scale. The sharp early drop shows rapid adaptation, and the slower decline later suggests the model is nearing a stable fit. The validation curve following the same shape is important because it means the improvement is not limited to the training batches. Track the solid training line and the dotted validation line. Both fall quickly at first and then flatten, which is the pattern you want to see when a model is learning effectively without immediate divergence. The two curves tell the same story from different angles. The training line shows optimization on the seen batches, and the validation line checks whether that progress carries over to new instructions. Loss is useful, but it does not fully capture whether the model gives a correct instruction response. The next step is to pull out the generated answers so their quality can be inspected and measured directly. A larger instruction dataset changes the scale of the problem, not the basic method. The same fine-tuning approach can be applied to Alpaca, but the extra size and length make compute and memory planning more important. Alpaca was one of the early widely shared instruction datasets, and its size makes it a realistic benchmark for fine-tuning. Using it means the model sees many more examples, so the training setup must be chosen with the available hardware in mind. With a dataset this large, GPU training is the practical choice because it reduces runtime substantially. If memory becomes the bottleneck, shrinking the batch size or the maximum sequence length is the quickest way to make the run fit. Fine-tuned responses are useful only if they can be inspected, compared, and evaluated after generation. This part focuses on pulling the model's answers out of the test set, checking them against the expected responses, and then saving everything for later analysis. Once the model has been trained, the test set becomes the place to measure how well it generalizes. The first step is to collect the model's answers for each test prompt, so they can be reviewed by hand before any scoring is done. The diagram lays out the workflow. First, generate responses from the test inputs, then collect those responses, and finally evaluate them. The important idea is that generation and evaluation are separate steps, so the answers can be inspected before they are scored. The first two stages of the final phase are about gathering evidence. The model's outputs are recorded on the test set, and then those recorded answers are used to measure performance in a more systematic way. The goal here is comparison, not just generation. Printing the prompt, the correct answer, and the model's answer together makes it easy to spot where the model is exact, where it is close, and where it drifts. The loop starts with just 3 samples, so the output stays readable while we inspect the behavior. The generate call produces the full prompt plus completion sequence, and then slicing removes the prompt so only the model's answer remains before printing it beside the reference response. Those comments mark the 2 parts that matter most. One limits the display to a small sample, and the other reuses the same generation helper from earlier, so the response extraction follows the same decoding path as before. The generated output includes both the prompt and the completion, so the response has to be carved out of the full string. That cleanup step matters because evaluation should compare the answer the model actually produced, not the instruction text wrapped around it. The side-by-side layout makes it easier to judge quality by eye. Focus on whether the model preserves the instruction, matches the target meaning, and stays specific enough for the task asked in the prompt. The comparison shows a mixed result, which is what usually happens in practice. 2 answers line up well, while one is only partially right because it names a related cloud type instead of the exact one requested. A chat model does not fit neatly into a correct or incorrect score the way spam detection does. The quality of a response depends on relevance, coherence, and usefulness, so evaluation has to look beyond a single label match. Benchmark suites like MMLU test broad knowledge with concise factual questions. They're useful when the goal is to see how much the model knows, not how naturally it converses. Human preference tests compare model outputs directly and ask people which response they prefer. That give a practical signal about conversational quality, especially when wording and style matter. Automated judging uses a second model to rate or compare responses at scale. It is not the same as human judgment, but it can make large evaluations much faster and more consistent. Each method measures a different aspect of quality, so combining them gives a fuller picture. For a conversational model, the most useful signals usually come from human preference and automated dialogue focus metrics rather than simple question-answer tests alone. Conversational performance is about more than getting the right fact. A useful chat model follows context, handles nuance, stays consistent, and adapts its style to the interaction. A strong response fits the conversation rather than just the literal wording of the prompt. That means the model has to track what the user means, not only what the user says. Manual review gives useful insight, but it does not scale well. Once the number of responses grows into the hundreds or thousands, the time cost becomes a real bottleneck. That scale problem is why an automated judging approach is attractive. Another model can score or compare responses quickly, which saves time while still producing a useful measure of response quality. An Alpaca-inspired setup keeps the basic idea of model-based evaluation, but uses the dataset that matches the intended task. That makes the assessment more relevant than relying on a generic benchmark alone. Saving the generated answers turns them into reusable evaluation data. Once they are stored alongside the prompts and targets, they can be inspected again later or loaded into a separate session without rerunning generation. The same generation routine is used again, but now it runs across every test example instead of just a few. Rather than printing answers to the screen, the code writes each one back into the dataset, so the file becomes the evaluation record. The listing turns the test set into a saved collection of model outputs. That makes the next evaluation step much easier, because the responses are already attached to each example. The TQDM wrapper adds a progress bar, while the loop processes every test example. After each response is generated and cleaned, it gets written into the matching dictionary entry, and the final JSON.dump call saves the full augmented dataset to disk. That indentation option does not change the data itself. It only makes the saved JSON easier for a person to read when the file is open later. The runtime is short enough to be practical even for a full test set. That matters because the generation step has to finish before any large-scale evaluation or comparison can begin. The progress bar confirms that every test example was processed successfully. It also gives a quick sense of throughput, which is helpful when the same procedure has to be repeated on larger datasets. A quick inspection of one entry is enough to confirm the data structure changed the way we wanted. Checking a single sample is a simple guard against bugs in the save step. Printing one dictionary entry reveals whether the new field is present and attached to the right sample. That kind of spot check is small, but it catches mistakes before the file is reused elsewhere. The printed dictionary confirms that the generated answer has been stored alongside the original instruction input and target output. That means each test example now carries its own model prediction for later analysis. The stored response is close in meaning, even if it is not identical to the reference. That makes it easy to judge whether the model captured the task correctly and whether the wording still stays within the intended style. Saving the weights means the trained model does not have to be rebuilt from scratch later. Once the parameters are written to disk, they can be loaded back into the same architecture whenever needed. The file name is cleaned up first, so it is safe to use on disk. Then the model state dictionary is saved with torch.save. That state dictionary contains the learned parameters, which is the part needed to restore the fine-tuned model later. Removing spaces and parentheses keeps the file name tidy and avoids awkward characters in the saved model name. It is a small detail, but it helps prevent file handling issues across different systems. Loading the save state dictionary restores the trained parameters into the model architecture. Once that file is available, the fine-tuned model can be reopened and used again without repeating training. Measuring a fine-tuned model means comparing its answers against a reference in a consistent way. The goal here is to move from a few hand-checked examples to a repeatable evaluation that scales to the whole test set. A small manual check can tell us whether the model looks reasonable, but it breaks down once there are many responses. A stronger model can act like a grader and assign scores across the full set, which makes the comparison much more systematic. Track the 3 stages in the pipeline. The fine-tuned model produces responses, the test set provides the reference answers, and a separate LLM assigns scores to those responses. That final scoring step turns a qualitative check into something we can measure. This last stage is where evaluation becomes quantitative. Instead of reading a few samples by eye, the model's outputs are scored so we can compare runs and judge whether training changes helped. An instruction-tuned 8B Llama 3 model is capable enough to judge another model's answers, and Ollama makes it practical to run on a local machine. That keeps the evaluation process self-contained instead of depending on an external service. Ollama is just a runtime that generates text from model. It is useful for inference, but it does not replace the training or fine-tuning tools used earlier in the pipeline. When a local model is not strong enough, the same grading idea can be pushed through a web API using a more capable proprietary model. The evaluation method stays the same. Only the model behind the score changes. A larger hosted model can produce even better judgments, especially when the task needs more nuance. The trade-off is that you give up the simplicity of running everything locally and rely on an API instead. The code depends on Ollama being available on the machine, so the first requirement is to install it and confirm the setup matches the operating system. Once that runtime is present, the rest of the notebook can talk to the model from the command line or from Python. On Mac OS and Windows, the application can run in the background and also expose command line access when prompted. Allowing that option makes it easy to call the model from a terminal or a notebook. On Linux, the installation is handled from the terminal with the command provided by the project. That gives you the same local model runtime without relying on the desktop application. Before any scoring code runs, the model server has to be live. Starting the app or running the service command gives the terminal something to talk to, and that quick check saves time later when requests begin failing silently. Focus on the two ways to keep the model server available. Either launch the Ollama app or start the service manually with the command line. Both paths lead to the same result, which is a running local endpoint ready for requests. The key detail is that the model must keep running in the background. Whether that happens through the desktop app or through Ollama's serve, the notebook can only query the model when that process is active. The command line test is meant to confirm that the model has loaded correctly before the notebook code takes over. If the service is up, the model should open an interactive session and respond to prompts immediately. This command asks Ollama to fetch and start the Llama 3 model. The first run is usually slower because the model files need to be downloaded before the interactive session begins. That initial delay is normal because the model is several gigabytes in size. After the download finishes, the same command opens the model much faster on later runs. The download log shows the model layers arriving, the checksum being verified, and the local manifest being written. When it ends with success, the model is installed and ready to use. The same local workflow can use different models if the machine has less memory or more compute available. Choosing the model is mostly about matching capability to hardware. The standard Llama 3 model is strong, but that strength comes with a memory cost. If the machine is tight on RAM, a smaller model can still be useful for evaluation even if its judgments are a little less capable. A bigger model can improve the quality of the scoring, but the hardware requirements rise quickly. At that scale, the choice is no longer just about accuracy. It is also about whether the system can actually load the model. Once the model is installed, the command line behaves like a chat window. A simple question is enough to confirm that the model responds normally before using it for scoring tasks. The response shows the model is alive and generating fluent text, not just returning an error or placeholder. A simple factual prompt is enough here because the goal is only to verify that the model can answer coherently. That variation comes from the model and runtime settings, so a different answer does not necessarily mean something is broken. For evaluation, that is why we later try to make the prompt and generation settings as stable as possible. Closing the interactive chat does not stop the underlying service. The notebook still needs the server process alive, so the safe habit is to end the session cleanly while leaving the model runtime active. A quick process check protects the rest of the workflow from failing later. If the service is not active now, the scoring code will fail when it tries to send requests. The loop walks through the running processes and looks for one whose name contains Ollama. If it is missing, the code raises an error immediately. If it is present, the final print statement confirms that the service is ready. A true result means the service is available and the notebook can continue safely. A false result means the model server needs to be restarted before any API call will work. Sometimes the notebook is reopened after the earlier setup cells are gone. In that case, the remaining code needs the data file and the helper function loaded again before scoring can begin. The helper builds the prompt structure the scoring model will see, so it has to match the earlier format exactly. Reloading the test data and restoring that function puts the new session back into the same state as the original notebook. The data file is loaded into memory, and the prompt formatter is rebuilt, so each example has the same instruction and input structure. That consistency matters because the greater model should see exactly the same prompt style for every response it scores. Calling the model through Python makes the scoring process easier to automate over many examples. The same prompt can be sent repeatedly, and the notebook can collect every returned score without manual typing. This function is the bridge between Python and the local model server. The important idea is that Python sends a JSON chat request, then reads the streamed reply back as text. The request body names the model, wraps the user prompt as a chat message, and fixes the generation options so the output stays predictable. After that, the code sends a post request to the local API and rebuilds the streamed response line by line into one text string. These labels point to the steps that matter most. Create the payload, keep generation deterministic, encode it for transport, send it as a web request, and read the reply as it arrives. That sequence is the pattern for talking to a local model endpoint from Python. The API call only works if the local service is alive at the moment the request is sent. A successful check here prevents confusing failures later when the scoring loop begins. The test call proves the helper function can reach the model and receive a normal answer. Once that path works, the same function can be reused for every evaluation prompt. The first line chooses the local model, the second sends a prompt through the API helper, and the third prints the return text. It is a compact end-to-end test of the whole request path. That output confirms the request succeeded and the model responded with a complete completion. A working answer here means the same helper can be trusted for scoring the test set. The important part is not the Llama fact itself, but the fact that the API returns a coherent multi-line answer. That tells us the local model is generating usable text, which is exactly what the grader will need later. Now the helper is repurposed from asking questions to judging answers. The scoring prompt compares the dataset's reference output with the model's response and asks for a numerical rating. A small sample is useful because it lets us inspect the prompts and the scores before spending time on the full evaluation run. It is a quick sanity check on the scoring setup. Each loop builds a scoring prompt from the input, the reference answer, and the model's response. Then it prints the comparison and sends that prompt to the grader so we can inspect both the score and the explanation it produces. The exact wording can change from run to run, yet the general pattern should stay the same. If the grader is working well, better answers should get higher scores and weaker answers should get lower ones. Focus on how the grader reacts to a reference answer and a candidate answer. The useful detail is whether it gives partial credit when the model is close but not fully correct. That behavior matters because evaluation is not always all or nothing. A response that captures part of the correct idea should score between failure and perfection, and that middle ground is often what tells us how close the model is getting. The detailed explanation is useful for inspection, but it is awkward for computing an average. Asking for only the number makes the evaluation easy to aggregate across the whole dataset. This version of the scoring code is built for batch evaluation. The prompt is tighter, the result is numeric, and that makes it possible to measure the model with a single average score. The function loops through every example, sends the grading prompt to the local model, and tries to convert the reply into an integer. If the model writes anything other than a plain number, the exception handler skips that item so the scoring run can keep going. That instruction line is the key change. It removes the explanation and leaves only the number, which is exactly what a summary metric needs. A full pass gives a more reliable picture than a handful of samples. Once every test example is scored, the average becomes a compact measure of model quality. The function returns a list of numeric scores. Then the code checks that every test example produced one and computes the mean. That average is the single number we can compare across runs and model versions. The count confirms that no examples were lost, and the average condenses the whole evaluation into one comparable value. That is the number to watch when experimenting with training changes. The progress bar shows every test item was processed, and the final line gives the average score for the fine-tuned model. That number becomes the baseline for comparing different prompts, datasets, or training settings. A score above 50 suggests the model is doing better than chance level or weak responses on this test set, though there is still plenty of room to improve. More important than the exact value is that the metric now gives a repeatable yardstick for future experiments. Because the local runtime is not perfectly deterministic, one run can drift a little from another. Repeating the scoring and averaging the results gives a steadier estimate of performance. Once the evaluation exists, the next question is how to move the score upward. The main levers are training settings, data quality, prompt design, and model size. Training behavior changes a lot when the learning rate, batch size, or number of epochs changes. Those settings control how fast the model learns, how stable the updates are, and how long it keeps adapting. A larger and more diverse dataset gives the model more situations to learn from. That often helps it handle prompts outside the narrow pattern it saw during fine-tuning. Prompt wording can change the quality of the response just as much as the model itself. Clearer instructions often steer the model toward answers that match the target style more closely. A larger base model usually has more capacity to represent complex patterns. If the hardware can support it, that extra capacity can translate into better responses after fine-tuning. Those reference numbers show why instruction tuning matters so much. The base model is already decent, but the instruction tune version is much better aligned with the kind of answers the evaluation rewards. The next step is to make fine-tuning cheaper by changing how the model is adapted. LoRa is a practical way to reduce training cost while keeping much of the model's capability. The exercise is about trading off efficiency and quality in a measurable way. Running the modified training loop and comparing both runtime and score will show whether LoRa gives a better balance for the setup. The main LLM workflow is complete now. Architecture, pre-training, and task-specific fine-tuning. The remaining question is what else you can build on top of that foundation, and what directions are worth exploring next. Those three stages form the core development cycle for a language model. Once that pipeline is clear, the natural next step is to look at optional improvements and resources that help you customize models or stay current with the field. The figure groups the process into 3 parts, and that order matters. First, you define the model structure. Then you teach it general language patterns, and then you adapt it to a task or instruction format. That label matches the development path we have been following. It reinforces that an LLM is not built in one step. It is assembled, trained, and then refined in stages. One useful extension is preference fine-tuning, which adds another layer after instruction tuning. The goal is not just correct answers, but answers that better match the style or preferences you want from a model. Preference fine-tuning is especially useful when 2 outputs are both valid, but one fits the desired behavior better. DPO is one practical path to do that, and the supplementary repository points to code you can study if you want to go deeper. The repository also includes extra material beyond the main chapter content, so there is room to explore more examples and related topics. That makes the book a starting point, not just a closed project. Staying current matters because model methods, tooling, and best practices change quickly. A good habit is to combine research papers with community discussion so you can see both the technical direction and the practical impact. Recent AR14 papers are useful for seeing where research is headed, while communities like our /local Llama help connect those ideas to real tools and experiments. Blogs from active researchers can also be valuable because they often explain new work in a more applied way. The closing thought is simple. Building a model from scratch gives you a much deeper understanding than only using one through an API. That hands-on path is what turns the pieces of an LLM from abstract ideas into something concrete. Working through the implementation forces you to confront the details of training, data flow, and model behavior. That kind of experience gives a foundation that makes later tools and papers much easier to interpret. For practical projects, tools like Axolotl and LitGPT can save a lot of effort because they package common training and fine-tuning workflows. They are good choices when the goal shifts from understanding every line to getting strong results efficiently. The field is moving quickly, but the core ideas you have worked through will stay useful. Keep building, keep reading, and those foundations will carry into whatever comes next. These final points pull the whole fine-tuning pipeline together: dataset preparation, batching, model loading, training, and evaluation. The goal is to turn a pre-trained language model into one that follows instructions reliably and can be measured in a practical way. A pre-trained model already knows language patterns, but instruction fine-tuning teaches it the response style we want. After this step, the model is no longer just predicting text well. It is responding to prompts in a more useful, task-oriented way. That process starts with data that is already paired, an instruction and the desired answer. The entries need to be put into the model's training format, then separated into train, validation, and test sets so learning and evaluation stay cleanly separated. Batching has to make different length examples fit together without confusing the loss function. Padding gives every sequence the same shape. Target token IDs tell the model what to predict, and the padding mask prevents those extra filler tokens from affecting training. The starting point matters because the model already carries a lot of general language knowledge. Using GPT-2 Medium gives a strong pre-trained base, so fine-tuning can focus on instruction following instead of learning language from scratch. The training loop works much like pre-training, but now the data represents instructions and answers rather than raw text. Each update shifts the model a little closer to producing responses that match the instruction dataset. Evaluation should check how the model behaves on prompts it has not trained on. One practical approach is to generate responses on the test set and have a separate model judge them, which turns output quality into a measurable score. An Ollama-hosted Llama model can serve as that automated judge. It reviews the fine-tuned answers, assigns scores across the test set, and the average score gives a compact way to compare performance across models or training runs.